Okay, thank you, Fermin. Okay, so I added a page to make a correction. So the second order formula that I put has an error. It should be f double prime of x. It should be what?
Fx plus delta x
F of x plus delta x
minus
minus
2 times fx
fx
plus
plus fx minus delta x.
divided by delta x squared.
Delta x squared. So this is what it should be. I don't know what it was, but this is what it should be. Sounds good to me. I can even remember it probably. Yeah, I can remember that. Okay, so this is the correction. But there was another question, and the question is, what can we do? Well, this is the second order approximation of the first derivative of the second derivative. Of the first derivative, no? This is f double prime of f prime.
No, f double prime of fx.
F double prime. Okay, so, and what is the question? What is the question or the problem?
So the question would be, if you derive the second order derivative of fx based on the first order derivative of fx, what you get is like this, which means you make the
Whether you have this 20.
20.
What is this? No,
2
2 delta x.
Yeah, yeah.
Okay.
So the first order will be like this. After the equations, it looks like this.
Uh-huh.
So which means for the delta x, it's a 2 times delta x from the
But
first
what
order
equation? So this is the second order derivative. Now,
Yeah. So if you derive the second order derivative equations from the first order derivative equations, you have this.
okay.
So which is not same, since the delta x from the first order derivative, which is
No,
twice larger than the second order derivative.
okay, I am confused. So there was an error here that now is corrected.
Yes.
And now you're giving me another formula.
Yes, so this formula is derived from the first order derivative.
But this formula is also derived from the first order derivative.
Yeah, but it's not exactly the same. If you do it again, you will find this is the one we get from the first order derivative. But people are using this one.
So,
There's a discussion about this,
uh-huh.
which makes the delta x here.
Okay, so there is another expression. There is another expression that says f double prime of x is equals to
this.
f of x plus 2 delta x minus 2 times f of x plus f of x minus 2 times delta x divided by 2 delta x.
No, 4
delta x. So 2 delta x squared.
Yes.
Okay.
Yeah.
So the difference is exactly the same equation. The only thing is, for here, you use delta x1, delta x1, delta x1. And here, you use delta x2, which is double, right? So I can write this equation, I can write it exactly the same if I call this delta x2. And here, delta x2. And here, this is, all this is delta x2. Yes. So it's the same. And the only relationship is that the delta x2 is equal to 2 times delta x1.
Yes.
Okay, so what is the problem?
So the question would be, so basically you're changing the steps from the first order derivative.
So what they're doing is now, let's say, and I don't know where this is going to go, but let's say I have here delta x1, delta x1, delta x1. And if I go in the blue from here to here, this is delta x2, delta x2, right?
Yes.
Okay, so, and this is the function of x. So you are basically doubling the step.
Yes.
Okay,
So
so what is the reason?
it's from the math.
Yeah, but you're doubling this. The equation is the same. The only thing you're doing is instead of using, let's say that the function had these points. So the function had this point. Let's start this point, this point, this point, this point, so forth. The only thing you're doing is I don't want to use the point in the middle. I want to use this one, and this one, and that one over there. So that's the only thing your equation is doing is skipping a point and making the discretization less fine.
Yes.
Okay.
So which means as a boundary at some point, so you're basically enlarging the space. So at the boundary at
No,
some
no, no.
point,
I'm not enlarging the space. The space is the same. So,
data to
no, you less data. So let's do it well here. You need less data. Now you need half the data.
No. So let's say you want to calculate the first let's say you want to calculate the first derivative of here, right? So you only need is those 2 points.
I only need those 2 points for
The first order
for the
derivative.
first order. No,
But
for
if
the
you-
first discretization. Both of them are the same.
Yeah, for the first order derivative, you only
No,
need these 2 points.
no.
But for a second order, you need more points go to beyond here.
Let's talk about the orange.
Orange,
Let's
yeah.
talk about the orange. The orange will take this point, and this point. Right?
Yes,
So it takes 3 points.
yes, 3 points.
Yes. The blue takes this point, and this point. Also takes 3 points.
No, but when you get the readings, you get this discrete.
From where you get these readings?
No.
Those readings you don't need to get them, you need to create them.
Yes, so you're basically creating more
So
more
I
love
have
of
the
curves.
function, I have the function, the orange function. I have it.
Yes,
And I can decide the discretization step.
yeah,
Okay. I can decide to use delta x1,
yes,
or I can decide to use delta x2.
yes,
Delta x2 is going to give me larger errors because I'm approximating it's basically a linear approximation what I have there.
yes.
So if I use the orange and you want to interpolate in the middle, say you want to get a point here, you're going to put a straight line from there to there.
Yes.
But if you use the other one, you're going to have a line that is from here to here. If you want to interpolate here, you're going to have a larger error.
Yes, but if you're using this one, so if you decide to use the delta x2, which matches the most popular equations, right? The delta x2 matches.
Delta x1 matches perfectly with my here. Delta x1 is perfect, and delta x2 is also perfect.
Okay.
But it makes a larger error.
Okay. If you decide to use delta x1 which is the most popular choice, then but that is the second order. For the first order, the delta x1
no. Both are second order. None of this is a different order. Both are second order.
Yes.
The order is from the derivative.
Yes.
So both are approximating a second order derivative. One of them is approximating the second order derivative with a smaller discretization than the other.
Yes. So which means for every order, if you want to do first order, second order, third order, which means you choose a different dot x.
Yes, normally yes.
Okay, then again,
Yeah.
yeah, okay.
But delta x depends in the end of how much these equations vary. Let's say that I have that equation. I put an equation that very nicely, let me push it to the left. I put an equation that I can very nicely do with a second order or with a linear approximation. But if I have this equation, let me show you this. If I have a behavior that is like this, right? Now, if I use a larger step, like the one for this, the one that you have, I'm gonna get this point, and this point. So the curve that this will predict is that, which is very bad. However, if I use, let's say, the red, I have this point, this point, this point, this point, and this point. And then my approximation is going to look like a linear thing, maybe green. It's going to look like this, which is much better. So it all depends on what is your delta. The more variations you have, the variation, the function, the more variation it has, the smaller needs to be your delta x. That's it. How good it is? Well, you need to take a look. So you have the plot of the function, and you need to take a look if you are discretizing it correctly.
Okay.
Yeah. Now, the methods of finite differences are very sophisticated. These methods are very sophisticated, and there are a lot of theory of differentiation. Differentiation is completely linked with finite differences. There are very complicated things. Probably the most advanced methods are smooth differentiators, of high order. I think it's Holbrook. I don't know the name, but Holbrook, something like this. Can you click in the internet, small differentiations, just to write the correct name here? Hol something. Small differentiations of okay. HOL. BO. RO. DK. Oh, all right. If you're really interested in knowing more about finite differences and these things, this is the guy who has made in the last 20 years the most progress on this. It's very sophisticated. Everything is just take derivatives, because sometimes
it's like an inverse one ejecuta.
so you can say so. Yeah. Now, sometimes, for example, when you take derivatives, I am going crazy on things that I shouldn't, but let me go a little bit. I'm going to go crazy in a little space here only. Sometimes your function is like this. Say it's a sine, and then it has some noise, and then it's a sine, and then it has some noise. This noise will magnify when you take the derivative. Yeah. So this noise, when you take the first derivative, you're going to get a function probably like this. So that is like a sine function. So you're going to get a cosine function. But in here, is going to have noise like this, magnified like that. And then it goes back and continue with the cost function, right? So that what this person has done is called smooth differentiators so that this noise disappears. And this noise disappears by taking more terms to the left and to the right. So, but so those things happen. I don't want to go into this because this is a course on finite elements, not on finite differences. Okay. All right. If you're not happy, see how we can stay after the class. All right. Okay, now I'm going to start with class 6. And I think the example that I want to take is it has even a name. The Dirichlet, this is an example, is the Dirichlet rectangle. This is a classical example that those who are solve problems analytically is the typical case. So I have a rectangle that is formed by 4 conductors. All the first 3 conductors are grounded. They are touching and grounded. And the last conductor has a voltage source applied to it. So it also goes to ground. Let me even remove this ground. Everything is there. So what it is you have an applied voltage at the top and everything else is 0. Everything's in the boundary. Then you go and develop the equations, you develop Laplace equation, blah, 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 and it's a typical problem solved by Laplace, right? And this is a problem where Laplace invented the Laplace transform and series. So they come here. So the solution of this is, of course, and this is being the voltage. So the first line at the top is at that potential, and everything else is at 0. So, and the solution is a series of functions here that have a, no, this is, I have to go more. This is closer to here, closer to there, and closer to there. It's something like that. So these are the solutions that give you from Laplace. And if you were to say the solution of B and X has hyperbolic cosine of the function and sine of the function. Yeah, it could be actually even sine sinh and sine. It could also be cosine x. One is of x and the other is of y. Yeah, all right. So it's a sum of them. It's an infinite sum in the terms of Laplace or Fourier transforms. Okay, this is a problem that I'm going to solve. There is analytical solution, and any advanced book on electromagnetics gives you the solution of this because that is a classical.
What is the purple?
The purple is conductors. These things are conductors.
Hollow or
Hollow. Yeah. It can represent, if you study a little bit of antennas, it's like it could be an antenna. It's a rectangular or square antenna. But it's infinitely long, so it goes like that, right? It's infinitely long. It goes forever. Or it's simply 4 conductors on a piece of paper, right? Say you draw these conductors in a PCB, right? The 3 conductors are touching, and the one on top is insulated at the corner, okay? And then you apply a voltage between conductor 1 and conductor 2. Fayaz, you need to stand. Stand, you need to stand. Don't sit. Yeah. Just stand. Otherwise, you're going to fall asleep. Like this, can't fall asleep. Because the moment you try, you're just going to So you need to put more energy into staying awake, and the best way is just to stand. Yeah. Pay attention and no problem. You'll see that it goes easy. Yeah. You're gonna be tired at the end of the class, but that's okay. You're tired already. Yeah. Okay, so imagine you print a PCB with a little conductor on top, and then three conductors in a rectangular way, and you put the thing, and you want to determine the potential in there of whatever material you have, except a conductor, and then you can come and measure it, right? Measure the potential. You could. Anyways, this is the example that I'm going to use because it's typical. So it's an electrostatic problem. But I'm going to put the equations later. So how it is, final elements is you discretize, because this is a beautiful rectangle. You discretize with triangles that they are all identical. You just put the same delta X and delta Y, and you get beautiful rectangles like this. Beautiful triangles. They are all well formed. They are all maybe even the same. So if they are all the same, they all have the same area. So you only need to compute once the area of the triangles, which is very good because it gives you efficiency. All right. Now, at the very end, what we're going to do at the very end? So all what we're going to do today is to come up with a set of equations like that. So we're going to come up with a set of equations that has the voltages that are unknown. If you notice here, we know voltages 1 to 8, and we know voltages 9 to, so we know the voltages at the boundary. So we know this voltage 2, we know this voltage, this voltage, this voltage, this voltage. Okay. But we don't know the voltages of the internal. So let's say we don't know, let me put them in red. We don't know this voltage, we don't know this voltage, this voltage, this voltage, this voltage, this voltage. So here we will have B10, B11, blah, 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 to B40, 39, all the way to B39, right? And on the right-hand side, we're going to have some relationship here, and then the voltages of the boundaries. So we're going to have B1, B2, all the way to B8, and then we will continue with the voltages up to B48. So this will be the boundaries. These are all internal nodes. Okay. And our job today is going to be to come up with a matrix. So all the class is going to be about obtaining this matrix. So today we will obtain the matrix. You need to have boundaries everywhere. Final elements is a bounded problem.
No, I'm talking about the equality, means how they are equal.
Well, they are equal because they are a conductor. So the problem here is a conductor.
That's your initial condition. That's it. So you set the voltage there when you set up the problem.
I have put here this source, right? You see the source here. I have connected the conductor on top.
What is on the left side and what is on the right side?
Left, bottom, and right all those three is a conductor.
Yeah, I know.
And
But
it's
the
grounded.
The top is 1 volt, the bottom is zero.
Zero,
The right and left is what?
zero,
Zero?
zero. They are connected. This is a single conductor. I have put here a single oops, not in purple. Not in purple. Let me even delete this thing. It is a simple conductor like this, very thick, very thick. It's all one conductor. All right.
The bottom and the top are not connected.
The bottom and the top are connected only through the battery.
Oh,
No, they're shielding. The bottom and top are shielding.
The bottom and top are not connected. There is a little space in between here
Yeah.
and here.
They are shielding?
What do you mean by shielding?
Or-
No, no. There is insulation.
air
There
space.
is insulation, air, a piece of rubber
Mhm.
or something that doesn't give you electrical connection.
Okay.
Yeah. And this is called the Dirichlet triangle. That's its name. It is so important in electromagnetics that even has a name.
But it could give you capacitance.
You can have capacitance, you can have whatever. Yes, you can compute a lot of things. But the thing is, this is the example that is used to solve the analytical way for the electrostatic field. So if you have taken an analytical course on electromagnetics, you would know about this one because that is the example. It's I would say, it's the mother of the examples, right? Everything starts there. Analytical solutions are great, but they are not too many. There is this book, analytical, it's called the Smythe book. Smythe is called Static and Dynamic Electricity. And that book has the solutions for everything that can be solved. If it is not there, we used to say it can't be solved. If it is there, the solution is there. But I've seen people coming up with solutions of different things that are not in Smythe. One every 2-3 years or every 10 years, somebody comes with an analytical solution of something that should be added to the book. But very few people and very few solutions for different interesting problems come up from time to time. Yeah. All right.
the blue line that are 45 degrees.
These are the triangles. I have, this is a triangle. This is another triangle. So what I have done here is discretized. Yeah. Remember, we need to discretize. This is finite elements. So these are the elements. So these ones are the elements. So this is an element. It's not infinite, it's finite. So, and that is what gives a name to this thing. This is an element. And of course, this is another element, and this is another element. So each one of these elements has, because it's the easier way to do it, a triangle. This case doesn't even need to have triangles, but the triangle is what we have been using and is what we're going to use for most of the cases. All right. So another important thing that comes to mind is if you look at here, this is 10, 11, 12, 13, 14, 15, 16, 17. And then the next one over here, the next here will be 18. And this will be 19. So what this is telling you is that here you're going to have something. How do I call it something? I'm going to call it an E. This will be E10, 10. And over here, I'm going to have E10, 18. And that determines the band. This matrix is a banded matrix. Or a banded matrix, yeah, a band matrix. Nothing outside. Here is all zero. Here is all zero. So, so special techniques to solve band matrix exist, and the band depends on the numbering of these things. So sometimes you go through a optimal reordering so that you minimize the band. Minimizing the band is not necessarily the most efficient, but it is definitely something easy to do to get efficiency. What you really need to do is to minimize the feeling. And it will depend on the solution method. If you're going to solve this with relaxation, then who cares? There is not even the band matters. If you're going to solve this with the Gauss elimination, then the band is important, but more important is the feeling. We'll look into this later on, maybe not today, maybe today, I don't know. Okay, so
That means on the first line there, you're missing the triangle that's in the bottom right.
which triangle? You're talking about
Higher, lower. To the right?
1, 2.
Yeah, that two, number two. Yeah, this thing, are you missing
What,
that?
what am I
Because you are
missing?
using E1010, E10, all the way to E10.
Because 1, 2, and 9, I know
Yeah.
these are the boundaries. So I know
So
that
that's the name of the point. Okay, that's the number of the point.
the name of the node.
The node, yeah. The
Yes,
node, yeah,
yes.
Okay, so E1010 means, with.
Something, a coefficient related to that point.
Okay, I see.
Okay.
Okay.
Now, these coefficients are these coefficients of this matrix are complicated expressions of triangle dimensions and locations.
Is that directional or it's just,
What do you mean by directional?
it's for that point, it's maybe it's different from to the outside
The-
and different.
For
direction.
that point, for let's say in particular, this point, I am going to use the dimensions of this triangle, this triangle, this triangle, this triangle, this triangle, and this triangle. The dimensions and the coordinates of all the three vertices of each triangle.
Okay.
Okay.
But if
It is a big mess, but very simple. It's only algebra.
But let's say if it's different materials in the.
There could be different materials.
have to be. Okay.
I don't care. I
it
don't-
could, okay.
It could be. I don't care what the materials are. yeah.
Oh,
At this point, we are not complicating our lives, and everything is the same material. Yeah. Typically, to make it better, it would be like a semiconductor or something. Yeah. All right. So the whole class today is going to come up to compute these elements. So the whole thing is about that. But there are also elements here, is. I call it them is because that's the symbol I'm going to use. Okay. So, but that is the thing. So this is final elements. Build a matrix, solve the matrix, and the matrix has to do with the geometry of the triangles. And that's it. Nothing else goes into the geometry, into this here. So this matrix is, you know, in this matrix, which is a function of triangle geometry. In particular, one thing that is very important for this is the area of the triangle. Okay. If you have a triangle that doesn't have an area, you will have a problem here, right? Because we're going to divide by the area. So all of a sudden, you're going to have a number that is a zero or an infinite or something that is going to give you problems. So that is a problem when you have, for example, a cable inside a duct. And let's say that the cable has the dimensions similar to the duct. Okay, then you have it. That is where you have potential problems because there cannot be here triangles, right? So those are the worst examples that you can find. The easiest one is the one I have put in there. Everything is nice, perfectly good triangles. There is none in that. But if you zoom into that, you're gonna have this thing, the conductor is red. You're gonna have the conductor like this, and the duct like that. So what kind of triangles you can draw here, right? These very ugly triangles. So those ugly triangles at some point even disappear. They call it degenerate. That is what creates problems. The degenerate triangles. All right. The example I'm going to solve is an electrostatic. Electrostatics, let me use a better color. Electrostatics are the curl of E equals to 0, the divergence of D equals to the density, we'll say the charge density, and we're going to have D equals to epsilon E, right? And we're going to use the potential. We're going to go by potentials, and we're going to use the fact that E is equals to minus the gradient of B. And to make my life easy, the first example, we're going to put this one is equals to 0. And the reason is because there is no charge here. There is no charge distributed in this thing. So I am going to use a that equals to 0. So and I'm going to substitute this guy in there. And I am going to get the curl of the diverge of the gradient of V is going to be equals to 0. And then I'm going to substitute D in here. I'm going to put D here. So it's going to be the divergence on epsilon E equals to 0. I don't want to put anything else in there. So this is the equation that I need to solve. That's it. That's equation. Those are the equations that I need to solve. Let me put E in here. I have this problem, this thing bugging me here. All right. So I have the divergence of epsilon. Let me put the minus here. The divergence of epsilon gradient of V equals to 0. And that's equation. That's it. I'm just going to put the sign out. And that's all I do. Minus divergence of epsilon gradient of V equals to 0. And this is the equation that I am going to solve with finite elements. So I am allowing for variations on epsilon. Epsilon can vary. Right? In this problem, it doesn't vary, but I am allowing for this to vary. If it doesn't vary, this will just give me the Laplacian of V equals to 0, right? If epsilon is constant, it gives me the Laplacian of V equals to 0. But I want to solve this equation. This is the one I want, not this one. This is Laplace. Tal cual Laplace equation. And that is the equation that is normally solved here, right? If you were to come over here you will solve Laplace equation inside. So that is what you will give there. And the solution is this, obtained by Laplace in 17 something. Yeah. All right. So that is the problem that I want to solve. So this equation I take with me. And I'm going to use Galerkin. And another way of, another name of Galerkin is scientific cheating. Yes. That's what we're going to do. We're going to cheat. That's what we're going to do, but scientifically, so that you can accept the cheating. So I want to solve this equation. I don't need to copy it. It's simply enough. Equals to 0. This is what I want to solve. Let me write it better. My handwriting is every time is getting worse. Divergence of V equals to 0. This is the equation that I want to solve. Then I assume, let us assume that V voltage of A, which in this case is a function of X and Y only, but I'm going to put it general as a function of Z2, is an approximation of V. So I would say, then if I come here and substitute VA, then it's different from 0 because it's just an approximation. Say you invented. Hey, it's your best guess. This is what I think is going to be. It's kind of very difficult to propose something, right? If you have an X, Y, and Z thing, are you going to propose a distribution? But you can't, really you can't. But if you know, for example, the solution of this thing, you already know an analytical solution to that, well, you may say, oh, I am going to put a function that is like that. But it's different from 0, but it's equal to some error. Now, in finite elements, we don't call it, and the same is in finite difference, we don't call this an error. We call it a residual. It's the error, right? You made an assumption, which is for sure is wrong. You evaluate the function, and then you get a residual. So the way we are going to do this is we're going to rewrite this equation and say, let me put another color. I don't know why the colors are not coming. We're going to get the same equation minus the residual is equals to 0. So if we can compute a residual that brings this equation to 0 by modifying VA, we have solved the problem. Right? The only thing we need to do is to get the residual to 0. So what we do is we operate on these two things. We're going to change VA in some scientific way. We're going to change VA such that R becomes, let me say, it's never going to get to 0, approximates, tends to 0. So we're going to change VA using different ways. There are two things that are important here. So we are going to minimize R in each triangle. So we're gonna get a particular triangle, we know the expression, and we're gonna say, we're gonna minimize R, the residual, in each triangle. Hoping that if R at each triangle is minimum, then R overall is also minimum. So we're going to take triangle by triangle by triangle, minimize each triangle, and hoping that the combined error then is minimum. Is it completely true? Probably not, but it's a pretty good solution. Remember, we are engineers. We don't want to get to the 100% exact solution. What we need is something sufficiently good for engineering work. If it has 1% error, 2% error, 5% error, I can live with that. Yeah. Yes.
So for the permittivity, you're using an arrow or permittivity?
This is, it's called epsilon. It's not error. This is the permittivity.
Okay.
So this is a good question because this can be confused with the error. Instead of using here, let me call it error so that we don't have that. And this is permittivity. So thank you, because that would have been very confusing. Okay. How Galerkin does this? Galerkin says the volume integral, this is volume, we're going to do it in a flat surface, so this volume eventually will come an area. But for the moment, leave it like this. So Galerkin, and this is if you want to call this the cheating. Galerkin says, if you minimize the volume of some, I will even put it, the cheating functions, the right name is the shape functions. Shape of what? Shape of the triangle. So it depends on the shape of the triangle. Shape functions, shape of the triangles. So it says you have these things for each element, the volume of each element, and you make it 0. So if you are able to compute these functions based on those triangles, compute these functions such that the error, the total error, because this is the residual, minimizes, then you get the solution. Now, you don't know what those functions are. So what we're going to do, most of what we're going to do is we're going to compute the shape functions. All right. If you go for 2D, this is for 3D, this is 3D. If you go for a 2D problem, then you will have, this is the area of the same functions, RK, dBk equals to 0. So this is, if you're going to do it in 2D, the only thing you need to change is the voltage. Now, this is to be determined. We don't know them yet. But if we are able to get them, problem solved. So that is what we're going to do. Try to get them. All right. I need that that equation. Remember I had The equation I had is epsilon BA minus R is equal to 0. Therefore, R will be equals to this. Watch out. We may try something like we are working in a circle, but it works. We are kind of working in a circle, but it works. Now, we're going to substitute this residual there, right? So in the volume, not in there. I want to keep it general. I want to keep it general just because at some point I want to use Gauss theorem. And Gauss theorem relates volume to surfaces, not surfaces to lines. So I want to keep it on this equation just to make it less complicated. And then we do it. Then we reduce the order as we wish. Okay, so I am going to substitute it there. So the residual becomes the divergence of the gradient of VA. And I am going to put this back into that equation. Oh, it was already there. So I put it back into this equation. So is the volume integral of the shape functions, what is it? Then the residual, which is the divergence, right? This should have been the divergence. Yeah, it's the divergence. So here I need to put a dot, the red dot is the divergence of that. Here it is the divergence of epsilon, the gradient of BA dV. All right. Then I'm going to use this identity to develop, of course, this, right? Here, that, and that. So I'm going to have two terms. Everything is going to be the volume of the WK, the cheating functions, and I am going to have F is epsilon, so two terms here. So two terms. Epsilon, the divergence of, no, it's WK. First is WK. F, and let me actually put it this way, yellow. F is WK, and let me get another color, and A is this, right? Okay, so WK I get out from this equation, and I get the divergence of epsilon BA plus A, which is epsilon, the gradient of BA, and the divergence of WK dV. Now I'm going to separate this into the two terms. Oh, no. No, but it's here, right? Like this. Yes. Yeah. Yeah, you're right. This is the right way. And now I want to separate the two terms. WK, the divergence of the epsilon gradient of that, plus the volume epsilon BA dot WK. And this is dV, this is dV, and the whole thing is equals to 0 as it has always been. equals to 0 from the beginning, right? From here. All right. Now that we have this, we can see that we can apply Gauss theorem to this. Which side? To this side. So this is the volume of a divergence, right? So this becomes the closed integral over the area of WK epsilon VA d V d area. This is applying Gauss theorem. Let's write Gauss theorem here, right? Let's write Gauss theorem over here. Gauss theorem tells you the volume integral of a divergence of something, of some vector, let's call it not V, let's call it vector F, dV is equals to the closed integral of that F, the surface of area. Okay, so F here will be this, right? This is F. The WK, well, it can be out if you want. We can take it out or we can take it, yeah, it's inside. WK. Okay. So the only thing I need to do is to remove I need to remove this gradient, right? This divergence and change the volume by area and the volume by area, right? That's all I'm doing with this Gauss theorem. Okay. Now, what is the meaning of this? So if you have your area here, say you have the problem here. This thing over here is the boundaries. Okay? So it's something that you know, because you're going to integrate over here, right? You know the values of all these things. So those are the boundaries. So basically that a term becomes known from the boundaries. Yeah. So the equation simplifies to the volume integral of E dot BA dot product of the gradient of this dV equals to something known. Let me call it known. Right? Yeah.
So for finding the error, for each block, we have to apply this.
For each triangle, you apply this. This applies for each triangle. But then you also applies also in the general term, right? When we saw a Gauss theorem, you probably remember that we discretized these things, right? And we eliminated all the internal paths of integration, and we ended up with only the outside. Yeah. So at the end, this is what you have. Any questions so far? So we are trying.
Sorry, Dr. Leon, in the equation of you correct boundaries is the gradient of BA.
Gradient of BA here. Yes. Yes, thank you. Still is the boundary. But yes, we need to make it correct. Yes,
About the question.
no, it's hold on. Gradient.
After both theorem, there's no gradient anymore.
After what?
After the Gauss theorem, there's no gradient anymore.
After the Gauss theorem, there is no gradient, no?
I thought you added a gradient.
Okay. I still have, no. I still have these gradients, right? I still have these two gradients.
Professor, is not the gradient of epsilon, is the gradient of BA. I don't know, I think because you're applying the
Okay,
theorem.
let me go back to where am I making the mistake here?
The Gaussian.
Okay, so let me see. Is this equation right?
Yeah, the next one also.
The next one, this one is right?
Yeah,
Okay, now we apply Gauss theorem,
the Gauss theorem, yeah.
and we need
And
to
divergence
and
disappears.
we need to remove the F, but F is all this, right?
Yeah, this is Nabla VA.
Okay, so this will be epsilon nabla VA. That's it. Okay. Still is the boundary. The thing is, at that time, I don't even want to see it. Okay. It has, let's put it correctly, but I don't want that term because I know it. Whatever it is, I know it.
I have a question
Yes.
about the first equation, like in the scheme.
The first equation here,
Yeah, the first one.
yes, is there. So what's the question?
Yeah, so how is the second part? The VA.
Oh, that comes from this analytic, from this equality.
Yes, then why?
So this is a vector equality, right?
If a YWK is at the end.
So the equation, we apply that equation to this, right? So F is WK.
Oh, F is
F is WK and A is epsilon gradient of VA.
Oh,
So the colors should tell you, right? This color is this one is this one.
Okay.
So, and then I only apply the equality. Let's only apply the equality and then it gives me this.
okay.
Are you okay, Fayaz? All right. Good. All right. Now, we're almost done. We're almost done with the crazy math. Okay. We are solving the problem in 2D. So this volume will have integral of on X, Y, and Z, but we probably don't want the Z. So we are going to solve it only for the area. The equation I just copied the same it is. The area equals to something that we know. I don't want to put any variable or anything. And what we're going to do is do it triangle by triangle. Okay. From before we have area of the triangle. And we're talking about a triangle that has coordinates X and Y. And it's like this, right? This is point 1 of coordinates X1, Y1. Let me put the coordinates in another color. The coordinates of here is X1, Y1. Here is X2, Y2, and here is X3, Y3. And we can actually even put the names to these vertices. This is going to be vertex 1, this is going to be vertex 2, and this is going to be vertex 3. And we have come up at the end with the area of the triangle will be 1/2 of the absolute value of x2 minus x1, y1 minus y2, minus x1 minus x3, and y2 minus y1. Okay. And you can do all what you want. That is, in the end, the area of this triangle. The area of this triangle is very important. So there is no more vector math in here. Starting from here, everything is geometry. From this point on, is only geometry. Geometry and algebra. Yeah, so nothing more is needed than this equation, nothing else. So, but it needs a lot of you cannot imagine how convoluted it's going to become with simple equations, but we're going to transform them that way, this way, the other way, backwards and forwards, and we're going to do a lot of little manipulations, all very clear there. But it's a lot of manipulation of things, right? The other important thing that I hope it was clear, but if not, we're going to make it here, is linear interpolation. Say that you do linear interpolation in 2 dimensions, right? If you have x and y, and you have a function that you know, let's say that is your function, and this is your function, and you know the points here, let me put them in black, and you know the points here, 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 right? You do linear interpolation, getting this will be x1, this will be x2, that will be y1, that will be y2. If you want to compute the value of the function in the middle, you do a linear interpolation. And the way we normally do is we say, let's say this is xi, and we want to compute yi. So we will say yi is equal to the slope of this line, right? Xi plus b. This is how we will get yi from the slope and the intercept, right? But now you don't have only one point. You have a little triangle. You have your triangle. Let me put it a little bit more crooked, a little bit like that. Come on. Now you have a triangle with the different points, right? This will be x1, y1, this will be x2, y2, and this will be x3, y3. And you want to do a linear interpolation to a point here and a point there. Instead of using only 2 points here, now you need to use 3. So the way that you would say is you are supposed to know, even though you don't know them there, is the volume here. So the voltage for a point x and y that is inside the triangle, so for a point bxy inside the triangle, I am going to say that this voltage is going to be equals to some part of ax, some part of by, or some part of y, some part of x, some part of y, and some c, right? So it's similar to this equation, except that I have a some coefficients. These coefficients I don't know. I don't know these coefficients, just like I didn't know m and v, right? You are going to compute m by saying y2 minus y1, x1 minus minus x2. No, x2 minus x1. And you're going to have an expression for b that I don't remember. I don't remember the expression for this b. But for the slopes, you have this. And you compute this by just extending the line. So you have the slope, you're extending the line, and then you're going to compute this b, blah, blah, blah. All simple trigonometry from high school. Or where do we get this? Analytical geometry, right? In high school. Or they have it in the university now. But
In college, I think.
I'm pretty sure.
It varies country to country.
It depends on countries. I think in
Yeah.
advanced countries like Pakistan, they teach it in high school.
Yes.
In countries, in bad
university.
countries like in the US,
Full
they teach it in university. But where did you learn it?
This one, AX plus BY.
No, that one.
It was in,
Elementary school.
yeah, it was in 11th class. It was in 11th class, like, we have 11th standard.
11th grade?
11th grade.
11th grade.
11th
Yeah,
grade.
that's probably when I took it too. For me, it was a high school thing.
Ninth
Yeah.
was-
It was analytic geometry. That is what,
You can say this is a high school.
We only have one book, math, that is called
only
math.
one book.
And it has all the entire.
All the maths from
derivatives,
from
matrices,
I see.
and all the things are put into them, and they are just naming chapters, it's matrix chapter.
Yeah, but you have to divide it in years. You have one book, but you take it for multiple years.
No,
Yeah.
we have two books of math, math 1 in grade 11,
Yeah.
math 2 in grade 12, that's it,
I see. Okay.
nothing else.
Well, in my high school, there were 6 maths. Math 1, 2, 3, 4, 5, 6. You had to go through this process. And it was okay. Yeah. All right. So the thing is that we're going to compute the values. The process is we want to compute this. We want to compute A, B, C from the values of B1, B2, B3, which will be whatever is here, it will be B3, whatever is here is B1, and whatever here is B2. So we're going to assume that we know those values, but we don't know them. That's exactly what we want to compute. So what we're going to get in the end is an expression. We want to get an expression of A, B, C as a function of V1, V2, V3. So at the very end, what we want is to reverse the problem. But let's say now, let's assume that we know V1, V2, V3 for the time being. Yeah. But of course, that's what you want to compute at the very end. So we're just going to reverse the equation at the very end. All right. So we set 3 equations. So we're going to say V of x1, y1 of x1, y1, which was equals to V1, is going to be A x1 plus B y1 plus C. And the same I do for B x2, y2 will be V2 equals to A, same A, x2 plus B y2 plus C. And the last one, B is x3, y3 will be equals to V3 equals to A x3 plus B y3 plus C. And this is beautiful because I have 3 equations and I have 3 unknowns. So I can write this equation like this, right? I can put it into a matrix. And I can put here x1, x2, x3, y1, y2, y3, and 1, 1, 1, and A, B, C, Let me write them a bit better. A, B, C equals to V1, V2, V3. And that's it. So I need to compute, or I want to compute. To compute A, B, C. So I need to take the inverse of this matrix. That's what I need to do. Take the inverse of this matrix, or go for the determinants, or go for whatever. I'm going to do one. I'm going to do only one. So let's compute the determinant. Let's call this matrix what name you want, what letter you want. It gives you the convenience to say the matrix. Matrix A. Matrix A. We use matrix A for everything. So the determinant of matrix A will be, we have already computed it before. It will be x2, y3. Let me not even put this. It will be x2, y3 minus x2, y2 plus x3, y1 plus, no, minus. And let me put these things clear. Y1 minus x1, y3. The determinant? No, for the determinant, I would prefer to go this way. I take this one, and then that, the multiplication of that minus that, right? So x2, y3 minus x3. This will be x3 minus x3, y2. So this is the first component, right? Then I take the other one. It's going to be negative. I take, let me put it in green. I take this one, and I'm going to get that one minus that one, but I need a minus one, right? So I'm going by the cofactors of this thing. Yeah. You could also go expand the matrix here and do x1, y1, 1, blah, 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 and go this way, right? You can also go that way.
This becomes perpendicular to the third point that you were proving previously.
Yes. I am not giving at this point a physical meaning, but it certainly has physical meaning. Yeah, but we don't need the physical meaning of this. So let me do then. X2, y3 minus x3 y2 plus x3, y1 minus x1, y3. Plus x1, y1, x1, y2 minus x2, y1. And, well, that's the determinant. After the end of the previous class, which was a couple of weeks back, Carlos and I stayed here and mathematically demonstrated that the determinant, this is the determinant of A, the determinant of A was equals to 2 times the area. Okay, so it's very nice because when you get the inverse, you just need 2 times the area. Now this is important, right? Because we're going to get the inverse of this matrix, so we're going to get the factors A, B, C, and they are going to be divided by the area. So that's why the area of the triangle is important. So if you can form this with good triangles, it's fine. But as I just mentioned, if you get to have another area, another, say, element of this that goes like that, at this point, you may not have good triangles. So if you need to go very fine, very fine, very fine, the area of this triangle is going to tend to 0. And because we're going to divide everything by the area of the triangle, when you divide by a small area, you magnify the errors and the problems and the convergence, and everything becomes complicated when these triangles are not don't have a reasonable area. Yeah. All right. So in the end, I am just going to write the values of my calculations. And by the way, if you don't believe me, go to Sikorski. Numerical methods, or I don't remember the name, but Sikorski has a book. Let me see if I can find it. Sikorski, and I think it's called computational, no, Sikorski, electromagnetics book. Engineering electromagnetics. What is this one? Fields and electromagnetics. No, this is not the one. But advanced electromagnetic theory, applied problems, primary electromagnetics.
Okay.
Yeah, you have my someone of you have my book.
Well, that green color book.
Yeah, it's a numerical solutions or something.
Oh, yeah, I have it.
Yeah. So
Can you grab it?
yeah, bring it, please. And let's everything I'm doing is with a Sikorski. Do you mean Sikorski electromagnetic field? Igor Sikorski electromagnetic fields. There may be another author, but Sikorski is included. Electromagnetic fields, wave and electromagnetics, classic. Numerical analysis. Yes. No, final elements. No, that's not the book.
The other one.
Okay, forget it. I have it. So I will take a picture and put it here. So everything that I do it comes from there. So go to the Sikorski, which now I just learned is with an O. Sikorski. Okay. Area. Value of A is going to be 1 by the determinant, and you're going to change the first row, B1, B2, B3, Y1, Y2, Y3, 1, 1, 1, and compute the determinant that way. You're going to get also B. B is going to be 1 by the determinant, and you're going to get X1, X2, X3, and you're going to be B1, B2, B3, and 1, 1, 1, and you get the value. And then the last one for C is going to be 1 by the determinant, X1, X2, X3, Y1, Y2, Y3, B1, B2, V3. Okay. And this is where you're going to get, well, you get the determinant. We can derive it easily if you want. 1 by delta, and you're going to get B3, Y3. No, B2, Y3. So again, we're gonna take the one. We're not gonna go crazy. We're gonna go this one minus this one, right? So is B2Y3 minus B3Y2 plus V3Y1 minus B1Y3 plus B1Y2 minus V2Y1. And that's it. And that's it for that one. Okay. I am going to rearrange this thing, rearrange it in the way that is most convenient for me. I am going to rearrange this by saying this is delta, and I'm going to get V1 as a common factor. So the elements that have V1, I'm going to put here, plus the elements that have V2 here. Let me give a little bit more space. V2 plus the elements that have V3 on this on this matrix, right? That's I told you it's a little bit too many little complications here and there, but everything can be followed. So everything that has V1 is first Y2. And V1 is also happening here, Y2 minus Y3. Right? That is simple to do. Then everything that has V2, I have Y3 minus Y1. Everything that has V3 will be Y1 minus and something I don't like it. V3 is Y2. Ah, no, see, yes, minus Y2. Minus 1 minus Y2. Yeah. Okay. So I leave it like this. To use the same nomenclature at Sikorski, this I will call it Q1. This one I will call it Q2. And this thing I will call it Q3. Just to follow the same naming in the book. And because I don't want to carry so much. So I'm going to start making these sorts of substitutions and substitutions and substitutions like that. The next one is 1 by delta, 1 by the determinant. And I'm going to have, again, the same thing. I get this one, that one minus that one, right? So I am going to get a V2 X3. I'm going to put it in black. V2 X3 minus, let me start with the X. X2V3. X2V3 minus X3V2. Then plus X3V1 minus X1V3. Then plus X1V2 minus X2V1. And again, I will cluster them as per V1 plus V2 plus V3. So I will cluster them like this. Everything that has V1, it will be here is X3. And the other should be negative minus X2. V3 minus X2. Then everything that has V2 will be X1 minus X3. Everything that has V3 will be X2 minus X1. And following the naming of these things, I will call it P. It's called it a QR. It's called R. In the book, they call this thing R1. This call this R2. And this call this one R3. The reason why I'm doing this substitution is because if I carry all these parentheses and parentheses, I'm going to make a mistake much easier than what I am. So far, I don't know how many mistakes I have made, but probably a few. 1 by delta. The good thing is that at the end, I am copying a little bit from my notes. So I will have now C. C, I am going to go right away to the final. So I'm going to go directly to the red. I'm going to go and get to the red directly. And I'm going to get it's a bit more complicated. It's going to get me x2, y3 minus x3, y2 that multiplies v1. And actually could be directly because you get this one, v1 times x2, y3, x2, y3 minus x3, y2. So it's easy, but it's already divided. Then plus, you're going to get v2. So v2, you're going to get x3, y1 minus x1, y3. It doesn't want to write anymore. Let me go and get the other part.
आज समझ आया कि क्यों बच्चों के अंदर ये खड़े हो जाते हैं।
आज समझ आ गई कितनी उससे बात समझ आती है दूसरे
Okay, this one writes. This one writes now. Okay, who knows? So x1, y3 plus v3, and this is going to be x1, y2 minus x2, y1. And this is going to be called P1. This is going to be called P2. No, P3. P3. And this one is going to be called P2. Okay. So if you were to put then the value of A will be 1 by delta Q1 V1 plus this is Q1 V1, then plus Q2 V2 plus Q3 V3. That will be A. B will be 1 by delta, and it's going to be R1 V1 plus R2 V2 plus R3 V3. And finally, C will be 1 by delta P1 V1 plus P2 V2 plus P3 V3. Okay, and remember, Q, R, and P are functions of x1 to x3, y1 to y3, right? So coordinates, these are coordinates of the vertices. Coordinates of the vertices. All right. Coordinates of the vertices. So you go to the triangles here, say, this is your triangle one, say, right? This is your triangle one, but let's not that one, this one. This is your triangle one. So the coordinates of this, so the x1, y1, this is the x2, y2, and this is the x3, y3, whatever the location of them is. Yeah, with respect to the entire thing. Yeah.
Why we have V1, V2, V3 matrix C? But
Say it again.
if you see matrix C,
Yes.
so the third row, why we have V1, V2, V3 there? But in the rest of the other, we don't have that. So
Okay, I'm not following your question.
I can answer that.
You
Can you show the other two? He's solving the system by determinants. So he's changing the location of B in every column, depending on which.
Oh, yes,
Kramer's
okay.
rule.
Yeah.
Yeah,
That's
exactly,
right.
exactly. So to compute A, you compute the determinant of the original matrix, and you substitute the independent number, the values of the right for the first column. Okay, in the second, for the second column, and on the third and the third column. Okay. Yeah, it's because you've been out of school too many years. Yeah, but remember, he's been working for 10 years doing useful things. So all these useless math.
Yeah, now we have computers.
Yeah. You don't ever do it by hand. You would go to your MATLAB, and that's it. But you have the perfect opportunity to check this with the symbolic calculations. Yeah. It would be great. And get a good symbolic, get Mathematica. Because that will give you the right thing.
MATLAB also has this.
Yeah, but MATLAB doesn't look good.
Yeah.
MATLAb, exactly. MATLAB doesn't give you true mathematical symbols. It gives you the right answer, but you need to interpret it. While the other way, you just grab the solution and paste it. But no. Anyways, okay. So now we have computed ABC. So if I were to put the voltage at a point as a function of X and Y, I will have AX plus BY plus C. And I am apparently know what is the value of A, B, and C. Of course, I don't know them because I don't know V1, V2, and V3 yet, but I can write this equation. How do I write this equation? I would say this is equals to 1 by 2 times the area of the triangle, because remember, the determinant is 1 by 2A. And here I will put the sum from I equals 1 to 3 of QI BI plus 1 by 2A, the sum from I equals 1 to 3 of R1 B1 plus 1 by 2A, the sum from I equals 1 to 3 of PI BI, right? I am just representing this thing as the sum of QI BI from I equals 1 to 3, all of them the same way. So this is the equation. Now, I'm missing the X and Y where?
After QBI and RBI.
QBI, I'm missing X here, Y here.
someone asked a question.
No.
Sure.
Somebody asking a question?
No, they don't. It was a comment of mine.
Por cierto, han producido al unir el Slack. ¿Quién sabe qué es eso? Sí, Carlos. Okay.
For tetrahedral, this will be.
No, 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 tetrahedrals, it's a different thing. Now you're talking about volume, right? So you will have to do all this for the tetrahedrals.
So it's just like 9.
It's gonna be the volume now.
Not,
Every,
not the 3 circles.
no, volume. So, hey, Fayas, this is a perfect opportunity for you to do it. I do the 2D simple. I mean, why do I need to complicate my life? What I need is to understand how it works. And if you understand how it works, let somebody else expand it for the volume, right? Or for different triangles, different ways. There is a higher order thing. So instead, you still use a triangle, but instead of using the values here and here and here only, you can also use the values here and here and here in the middle. And that is a second order that will give you, instead of a linear interpolation, a quadratic interpolation. Okay. And that allows you to make the triangles bigger. Okay. So, but we are not going to get into that just yet. Okay. What I need is to finish with this thing because it's already getting too much. All right. I need to expand these equations now because I want to X, Y, and Z.
Do the matrix.
I do the matrix, but the other way around. I need to rebuild the matrix, but now using the V's as the unknowns. So instead of being the ABCs unknowns, I need to now expand this, and it's already a little bit incorporated into the into here, right? So let me see how I'm gonna go. I am going to write B of X and Y is going to be 1 by 2A. This is going to be a long equation, right? And I'm going to put, I think I should put the value of A. And A is going to be Q1V1 plus a Q2V2 plus Q3V3, right? So this is, and this multiplies yeah, that's the way it is. Plus 2 and X. Yeah. Then I will have R1V1 plus R2V2 plus R3V3 Y plus 1 by 2A P1V1 plus P2V2 plus P3V3. That's it. So now I am going to separate. I don't like the fact that I have the X and Y, but let me see. I'm gonna write the same equation, b, x, and y. I'm gonna write it in this way. I want to write a function, whatever that function, I'm gonna call it a phi, function of x and y, v1. Yes, plus a function of x and y, v2, plus a function of x and y, v3. So now I'm going to concentrate it in the other ways. This way was concentrated as per ABC. Now I want to rearrange them as per V1, V2, V3, right? That's what I want to do. So what is this function? So it's going to be 1 by 2a, and it's going to give me, for V1, it's going to give me P1 plus R1 plus V1. But I need to put the X and Y and Z. P1 plus Q1, let me put the P at Q1X plus R1Y. Okay, that would be, and this multiplies to B1. Plus 1 by 2A, rearrange this and multiply by B2. Is going to be the R. So P2, V2, so P2 plus Q2X plus R2Y. And the other one is 1 by 2A, and it's going to be P3. P3 is the same thing, plus Q3X plus R3Y and multiplies V3. Okay. So these things here are the shape functions. And they are a complete mess of the coordinates of the triangles. Right? That's what they are. It's a complete mess of them, the coordinates of the triangles. So P1, remember, P1 comes from here, right? P1 is defined here. So it has x2, y3 minus x3, y2. So that's only P1 over here. So each one of these things has a complicated thing. So these are functions of the coordinates of the triangles. Functions of the coordinates of the triangle vertices. That one, and that one, and that one, and of course, the ones below, because they are the same. All right. So those are the shape functions. Okay. The last step is I need to go back to the beginning. I need to go back to the beginning here. Well, not quite to the beginning, but here. I'm going to need this pink equation here. I'm going to use this equation. What? Yeah, it's too many triangles. You also need to stand up. Too many little triangles. Okay. Well, actually, no, I'm not gonna come here. I'm gonna go to the beginning. Right here. This. What I have computed is that. Okay. So that is what Galerkin tells you. So go do all this mess and come back and put it there. So, yeah. Okay. So the whole mess is a big mess, but it's a simple mathematical, logical calculation of craziness. But there is no cheating at that point. Everything has been kind of a straightforward on the level. I've been not passing fast ones, but now comes the fast one. I am going to go and put those shape functions here, and that is supposed to guarantee the solution, right? So that is, remember, I used the word cheating. So what I do now is on that equation, put these things. So now I come and say, put the shape functions there. So I have the volume integral of W, let's call it now X, Y, and Z, and the residual of X, Y, and Z, and it's going to be dx, dy, dz, and this is equal to 0. Yeah. And then, what is the volume? Over the volume. If you want to be over X, over Y, and over Z. That should actually put it reverse. Over Z, like this.
How will you change to the volume for
I am, well, you want to remove the, I remove it. Well, you want it like this? You're happier like this, Fayaz? Provided that you're happy, I do whatever. So for Fayaz, remove the volume and stay in the surface. Yeah. All right. Thank you, Fayaz. All right. Now, these are called many things, right? They are called the Galerkin, the relating weights, or just the weights, or the shape functions. All right. So what this does is these functions give the right weight, or if you want to see this, the right correction, such that the error is minimized. The error in each triangle is minimized. Very good. We're almost there. We're almost out of time, but I think I'm going to stop there because there is more craziness to come with more triangles and more of those things. But I'm going to stop there. I cannot do anything else in 2 minutes. Yeah. Yeah. So, all right. So if there are any questions,
In simulation, there is the option of like sometimes the simulation will not work. Then they play with correction and tolerance things. Like we face a
no, that has to do with the solution method that we will see next time.
It's not related then.
It is related to this, most importantly to the area of the triangle. You have the console gives you a quality measure of the meshing. Yes or no?
Qualitative.
When you do the meshing, it gives you a number related to the quality of the meshing, how good the meshing is. Mostly is related to how bad or how small the area of the triangles is.
So in that case, like when we have a complex, let's suppose deformation thing, so there was very small meshes. So when we were putting the increase the tolerance or correction factor, then the simulation converges as it was giving the.
Yeah, so it depends on the method. I am only going to write the matrix, and then next class, I will go with what methods we have to solve for the matrix equation. How are we going to solve that? There's many things, many ways to solve it. It can be done with iterations. It can be done with a factorization. It can be done with a Krylov subspace methods. It can be done with many possibilities. The one I like is relaxation. That's the one I like. Just a simple relaxation, because the matrix is very big, but the matrix could be, I don't know, say that you have 100,000 triangles, right? So it's going to be 100,000 nodes. Say 100,000 nodes you have, or 10,000 nodes. But there are just a few elements in each one of the rows. So why don't you just solve them like this?
And we are referring nodes to the vertices.
To the vertices, yes.
But,
To the vertices of the elements.
if two meshes are like side by side, so they are sharing a common node. So this is like a repetition, more repetition.
More what?
More repetition of variables side by side meshes are.
Well, it needs to be, you need to discretize the median and continuum. So there needs to be for sure vertices that correspond to more than one triangle. At least two, but it could also be 6 triangles. So you can have 6. So you will have 6 elements on that row. All the neighboring elements play a part with one particular number. Yes, Chico.
Okay, so we're seeing the W, X, Y, Z in the sheet,
Shape function, the ones that we have just computed.
Yeah, so the W, X, Y, Z would be equal to, V, X, Y, Z.
No, these W's are this over here.
Yes, so yeah, the BXY.
So this thing is this thing.
So V, X, Y, right?
Okay, yes, the XY. All right, if that's what you want to say that way, yes. Yeah. So we finish this craziness next class. And at the very end, the only thing you really need to remember is that we're gonna have a matrix that gives you the solution, and that the matrix is a constant matrix if the medium is constant, a constant matrix that depends on the coordinates of the triangle vertices. That's it. A big mess coordinate, because I haven't finished mixing them. I still need to mix them a little bit more. So we get the A's, we get the P's, PQRs, then we get the shape functions, and then at the end, we're going to get the E. Is where it ends. In the E is the sum of the Q's, a multiplication of the sum of the Q's of P's and R's. You will see.
Like, V equals AX plus EY plus C. That is,
inside the triangle,
that is not just geometry, that's just
interpolation. That is interpolation, but that is inside the triangle. And you will compute that only as a post-processing. In the normal processing, no, you don't have a you don't have that. You only compute initially the results of the field or the potential in this case at the vertices of the triangles.
oh,
So, and then once that you have that, using the ABCs, you interpolate inside. Yeah. Okay. All right. We can stop this if there are no questions. Stop share. And no questions on the Mexico side, huh? There's nobody there.
No, thank you.
Okay, thank you for me. Thank you, Guillermo. Gracias. Bye-bye.
Bye.